Welcome to Complexity Made Simple, and in this video newsletter, of course, we're up to video 5 in the Catapult case study. So I said in the last video that what we're going to give you is some advice about doing process flow, cause and effect in real life, because the Catapult exercise is a great exercise to run, but it's not really like real life. So what we're going to do is add something onto the cause and effect diagram. So you're not just identifying inputs. So everything on the cause and effect diagram should be an input to your process, and then you're going to evaluate it for, is the variable controlled or not controlled? Now, you've got lots of control systems in your business, ISO 9000, you've got standard operating procedures, all sorts of things. So maybe some of your variables will be in control, but they should all go on the cause and effect diagram regardless. So let's get into this. Let's give you some advice on how to annotate your cause and effect diagram so you know which variables to fix, which variables to leave alone. Okay, we've got the 4 key process thinking principles now out on the table using process flow, cause and effect. It's the most important technique I've ever learned. But what we need to do is to bring that exercise into the real world, okay? Because if I took you out to one of your processes right now and we said, let's go process flow, cause and effect, let's find all the variables, there is a chance that some of the variables, maybe they're already under control. Maybe they already have a standard operating procedure. And therefore, we don't have to work on them. We've already got a rule in place and we're already happy with that rule and that it's getting used. Now that's the reality of the situation. In the Catapult exercise, because we didn't give any specific good standard operating procedures, there was no printed documentation, there was no auditing process, there's a good chance everything we identified in the exercise is going to be out of control. That's not going to be true in the real world. So when we do the analysis, I still want the variables to go on the cause and effect diagram. So a key point, your cause and effect diagram, you know, men, machines, method, material, measurement, environment. What this diagram is always going to be, and of course you've got your effect, your problem that we're trying to deal with here. What your cause and effect diagram is always going to be is a complete picture of all of the inputs to your process. A complete picture. It is not a picture of problems. We are going to put every input variable that we can think of on that diagram. Now then, if we find that the variable, so let's go here and we'll just call it, I don't know, the clean down procedure, one of the input variables. The clean down procedure. If we decide that the clean down procedure is already under control and we don't need to do any further work on it, what we are going to do to tell us to leave it alone is we're going to put a C next to it. We're going to put a C next to it, and that tells us that that variable is under control and we don't need to worry about it. Now then, an important point though, we're not just going to willy-nilly go around putting C's next to the variables because we don't want any work to do. If you are going to put a C next to a variable, there are 3 rules that must apply. First of all, you must have a standard operating procedure. Now, it doesn't have to be a piece of paper, but there has to be a control in place. So you might have an automated alarm in place, for instance. That's not necessarily a piece of paper, but it is a control. So you have to have a control in place for there to be a C. You have to be happy with the control. In other words, the standard operating procedure, the rule that you've got, everybody agrees that it works. Everybody agrees that it says something. So for example, if you read your standard operating procedure and it says something like, the technician should adjust the heat until they get a good result. That is a bloody awful standard operating procedure, and I would not be happy with that. That is not control. That is just an half-arsed description of what you currently do. Read your standard operating procedures and see if they are any good. And by any good, what should they be? They should be clear and unambiguous. Clear and unambiguous. So for instance, with a temperature, it's very simple. You say the temperature will be at 183 degrees. Clear and unambiguous. If I set it, the temperature will be at 183 degrees. If anybody on this course sets it, the temperature will be at 183 degrees. That is a variable under control. If you write down the technician can adjust the temperature until they are happy with the result, we could pick 10 technicians and we would end up with 10 temperatures. That's not under control. Okay, so you have a standard operating procedure. You are happy with it. It is clear and unambiguous. And finally, you use it. Okay, so it's actually applied. So you go out and when you look at the temperature, it actually is at 183 degrees. Now, if you can tick all three of those, you get a C. If you fail in any one of those, you don't get a C. Looking at slide 33, folks, we are down the bottom of that slide. If you don't get a tick in all three of those areas, you need to put N next to your variable. N, whereas C stands for control, N stands for noise or not controlled. The N's are where chaos lives. The way to think about your N's, by the way, and the way to think about chaos, it's like a handful of dice every day. So every day you pick up your 10 variables that you haven't got any control of, and every day you roll 10 dice on the table. You get a particular result. Sometimes it's a very high result and you're not happy. Sometimes it's a very low result and you're deliriously happy. But most of the time it's somewhere in middling, but it's bouncing around all over the place and you don't know why. You can't find a root cause. It's because you've got too many variables just bouncing around in your process. So if you can't tick these three, you have to put an N. So you do the cause and effect diagram. You put everything on the cause and effect diagram. You assign N's and C's to all your variables. And then here's what you do. You turn as many N's into C's as you reasonably can. If it is a variable that you don't think you can fix, leave it alone and stop talking about it. What everybody does, they talk about the variables that they have no control over. It's the weather. It's raining today. All the raw materials are going to soak up the moisture in the air and the process is going to behave differently. And the process is going to produce lots of defects and there's nothing we can do. Now, there isn't really too much you can do about the fact that it's raining. But if you talk about those things, that's a dispiriting meeting. You are never going to fix those variables that God is in control of. What you need to do is to talk about the ends that are in your gift. So back to that diagram I drew before. You've got a process. It's a money-making process. You have many, many variables. Some of them C's, but a lot of them will be N's. If you have a variable that you can't fix, that's okay. Ignore it. Work on these that you can fix. Think about it. If you remove variability from the input, what will happen? The process has to get more consistent. More consistent means predictable. You are going to turn as many N's into C's as you reasonably can. And then finally, on that slide 33, you have X. If you put an X next to a variable, X stands for experimental. You are going to do an experiment on your process to understand it better, and this is where excellence lives. So N is chaos, C is control, X is excellence. Predominantly you will see C's and N's on your cause and effect diagram. By the way, everybody's project, the cause and effect diagram is mandatory. All the other tools, I will let you choose some of the other tools, but process flow, cause and effect, NCX is mandatory. Everybody's got to identify all the variables. Everybody's got to say what current control the variables are in, and then your project plan is to fix as many N's as you reasonably can, and just watch what happens to the process. It's physics. You fix the inputs, you'll fix the output. Okay, so there you have it. The addition of C, N, X. This is controlled variables. You can leave these alone. These are uncontrollable, uncontrolled, or noise. They're the ones that you need to fix. And X is when we come on to experiments. And we'll be doing that on the Catapult soon enough. So these two are the ones, turn as many N's into C's as you reasonably can. So let's quickly just take a look at a case study. I'll just show you this. Obviously in the Catapult, I didn't need to do this because everything was an N. But let me just show you a case study where someone has identified the variables and put C's and N's next to their variables. Let's show you now. Okay, so here we are. It's a very simple case study. You can see someone's done a capability study, 40 pieces, hands off. You can see all the chaos without touching the machine. The machine is swinging from top to bottom on this particular process. And then the engineer concerned is going to do a flow diagram followed by, he doesn't actually do a cause and effect diagram actually in this. I'll show you that now. So there's his original flow diagram. What he actually does is he decides the setup is too complicated. This is a couple of hours of work in that one box alone, and therefore he decides to explode the setup into its own flow diagram. There is the flow diagram, and then you can see, look, out of every box he's identified variables that are in that step of the procedure. If you look at this, you can see, look, there's a couple of C's there, look, which is the wheel type and the wheel grade that is used in this process. But the amount of weight on the hub, the weight position, the center hub not torque value, not controlled. You can see all the ends over here, look, not controlled. There's one C, look, material. So lots of ends. Then this person puts those variables on a variables control plan, designs the controls. Lots of standard operating procedures are needed. There's some mistake proofing devices. There's a special action, and there's a fair bit of TPM. So this is the basic, taking the chaos out of the process. And once all those controls have been put in place, we get a much better performance. There is the new performance. So very much a transformation from where we were originally. There's our original performance. There's our new performance. A complete transformation of the physics. A complete transformation of the physics. That's what you're trying to do. You're trying to make your process produce a new pattern. And the only way to do that is to control input variables. Okay, so that's the end of video 5. So what we've gone through in the Catapult case study so far is we did exactly as that case study showed us there. We took a small number of pieces, hands off, identified whether we were in chaos or control. Once we identified we were in chaos, that means that we've got to pull the cause and effect diagram out of the toolbox because we've got to stabilize the process. You saw someone there stabilizing the process. We've also stabilized the Catapult process by identifying some good process controls. The use of CNX needs to be done in real life, because in real life, maybe you've got some standard operating procedures that control a nice portion of your variables. Well, if that's the case, where do you want to concentrate? We want to concentrate on the variables you haven't controlled. Go and work on those. Make a control plan and make the chaos disappear. But CNX brings reality to the situation. The Catapult didn't have CNX because everything was out of control. But in real life, we need this technique. And remember the 3 rules for this. Do you have a standard operating procedure? Are you happy with it? And do you use it? If you can't tick all 3 of those, you're not in control. You're down here. And that's where most of it goes wrong. You've got standard operating procedures, but nobody's using them. Nobody's read them for ages. Maybe nobody can understand them. And therefore, you're really here and not here. CNX. That's the latest bit of information in the Catapult case study. And I'll see you next week in video 6.